Okay, so today we're going to talk about specific heat capacity. Um, so basically the idea behind specific heat capacity is, let's say you've got two objects and you heat them. And let's say you've got two objects and you add 200 joules of heat to both objects. Now, just because you add the same amount of heat to both objects doesn't necessarily mean that you'll have the same outcome. Okay, and so when you talk about adding heat and changing the temperature of an object, how much heat you put in is obviously a factor that affects how much the temperature changes by, but there's also some other factors as well. Namely, what is the material of the object that you're adding heat to? Okay, so this is where the concept of specific heat capacity comes in. Basically, the way specific heat capacity is defined is, it's here on the slide. The specific heat capacity of a substance is defined as the amount of thermal energy, that is heat, required to raise the temperature of 1 kilogram of the substance by 1 Kelvin, or you could also replace 1 Kelvin with 1 degree Celsius. And so different types of materials have different specific heat capacities. For example, water has one specific heat capacity, ice has another specific heat capacity, aluminum, copper, all different types of material have different specific heat capacity. And you can read what the definition says, but essentially this is a number that tells you if I want to change the temperature by 1 degree Celsius or by 1 Kelvin, and I have 1 kilogram of that substance, how many joules would I have to add or remove to change the temperature by 1 degree? In other words, the higher the specific heat capacity, the harder it is for that substance to have a change in temperature. Okay, and so for reasons that I don't understand, the symbol for specific heat capacity is a lowercase c. And so now what we're going to do is we're going to look at doing some calculations with this. But first, let's take a look at this chart right here. Okay, so this is just a chart I found online, and it has listed different substances and their specific heat capacities. You can see that the unit for specific heat capacity is joule per kilogram per Kelvin. Okay, remember the -1 exponent indicates those things are being divided. So this is joule per kilogram per Kelvin. Okay, you also can see this as joule per kilogram per degree Celsius, and there's other units you can have for specific heat capacity as well. But if you look at this chart, you'll notice, well, a couple things. First of all, look at this chart. What materials or what substances have the lowest specific heat capacity on this chart? Okay, hopefully you said either platinum or lead. Both of those have a specific heat capacity of 130, tungsten 135, mercury 140. If you look at this chart, you should notice that the substances that have the lowest specific heat capacity tend to be metals. And there's reasons for that we're not going to get into now, but metals tend to change their temperature very easily. Okay, that's why they have the lowest specific heat capacity. If you think of cookware, this is why most cookware is made of metal. Right? Because when you put it on the stove, you don't want to take it. You don't want it to take a long time to heat up. You want it to be able to change its temperature very quickly. Now, keep in mind that it works both ways. If an object has a low specific heat capacity, that also means that its temperature can decrease very quickly. Right? That means it gives off heat very readily. Please don't overthink the name of specific heat capacity. A lot of people think, oh, capacity, that's how much heat something can store. No, it has nothing at all to do with storing heat or anything like that. The definition of specific heat capacity is what it is. It is the amount of energy required to raise the temperature of 1 kilogram by 1 Kelvin. Okay, that's it. It has nothing to do with energy storage or anything like that necessarily. If you look at this chart at what has the highest specific heat capacity, hydrogen is up there, and then besides hydrogen we have seawater, regular water. Those tend to have very high specific heat capacities. In fact, water tends to have a very high specific heat capacity, which is good because that means, well, a couple things. Number one, a lot of the weather comes from heat being absorbed or released by the oceans, because most of the Earth is covered in water. And so the fact that water has a very high specific heat capacity means that the temperature of the oceans change very slowly, either warming up or cooling down. which has some kind of stabilizing effect on the weather. If water had a very low specific heat capacity, then theoretically we might see some like crazy amount of storms coming from like rapid temperature changes in the ocean, but we don't see that. And of course, living organisms such as humans are made mostly of water, and the fact that water has a high specific heat capacity allows us to more easily maintain our body temperature, which is good for us if we want to stay alive. Okay, so what we're going to do now is doing calculations with specific heat capacity. And we have an equation to do calculations with specific heat capacity, and it should have been one that you've seen before. Okay, so here is the equation. Q equals mc delta T. Okay, I'm sure that everybody has seen that equation before. So just to recap, Q is heat. Okay, Q is heat that is measured in joules. Keep in mind that Q, which is heat, can either be a positive or a negative value. Now, just to be clear, heat in this context is a scalar. It does not really have direction. However, it's kind of like work, where you can think of a positive Q as heat going into an object and a negative Q value as heat being removed from an object. Okay, so just keep that in mind about heat. Next we have M, and this is mass measured in kilograms. Okay, heat is measured in joules. Mass, of course, is measured in kilograms. Then we have C, which is specific heat capacity. That's what we've been talking about. And then we have delta T. Okay, delta T is change in temperature. And we've talked about this many times before, but change in anything is always the final value minus the initial value. Now, basically what this Q equals mc delta T equation allows us to do is calculate how much heat does it take to increase the temperature of an object by a certain amount. Okay, so we typically deal with temperature changes when we add or remove heat from an object, and this is the equation that lets us do calculations with that. So do keep in mind delta T being a change in temperature can be a positive value or it can be a negative value. Now, one more thing before we get into some calculations, I also want to point out something about the units for temperature. Any equation that has temperature in it must the calculations must be done in Kelvin. But this equation does not have temperature in it. It has change in temperature, and that's a little bit different. So the corollary to that is any equation that has delta T in it can either be in Kelvin or in degrees Celsius. It has to be one of those two. And again, this is only for delta T. If you ever see an equation that just has T by itself, the calculation should probably be done in Kelvin, not degrees Celsius. As long as it's a change in temperature, it doesn't matter, because it turns out that delta T is the same in Kelvin as it is in degrees Celsius. And if you don't believe that, then you can try it out on your own. The reason for that is the Celsius temperature scale and the Kelvin temperature scale are basically the same, other than a constant value of 273.15. And so when you take the difference between two temperatures, that 273.15 kind of cancels out when you subtract the final and the initial temperature. And so it turns out that delta T is the same in Kelvin as it is in degrees Celsius. Okay, so there we go. Now we're going to do some examples with calculations. So let's take a look at example 1. Example 1 says, how much thermal energy is required to raise 5 kilograms of water, which has a specific heat capacity of about 4,200 joules per kilogram per Kelvin by 15 Kelvin. Okay, so we want to add heat to an object. How much thermal energy? That is Q. Okay, remember heat is the transfer of thermal energy to or from an object. Here we have the mass of the water. We're told that it's water, but we're also given the specific heat capacity. So that is a lowercase c. And then it says to raise the temperature of the water by 15 Kelvin. Now they're not giving us a temperature exactly, they're giving us a change in temperature. Okay, that 15 Kelvin is delta T. because it says we want to raise the temperature by 15 Kelvin, but it doesn't say what the starting temperature was. So they're actually giving us delta T there. So this is a very simple calculation. We're just going to do Q equals mc delta T, and I'm going to go to my calculator, and I'm going to plug in. So mc delta T, Q equals 5 times 4200 times 15. And when I type that into the calculator, I do get a big number. That is 315,000 joules. Okay, and so that is the answer to question 1, which is a very simple type of calculation there. Now, of course, remember what we've been talking about in the last couple of videos is that temperature is a measure of the average kinetic energy of the atoms or molecules making up a substance or making up an object. So what did we get, or what happened when we added this 315,000 joules to the water? Basically, the water molecules are now moving faster, right? On average, each one has a higher kinetic energy. Okay, so don't forget the conceptual understanding of what this actually means. Okay, so let's go on to the next example. Example 2 says how much heat is released when a 12 kilogram hot piece of iron with a specific heat capacity of 450 at 250 degrees Celsius cools down to a temperature of 170 degrees Celsius. So heat is Q. If heat is being released, we would expect our value for Q to be negative, and it is actually going to be negative, and we'll see that in just a minute. So here we have the mass of the iron. We're given the specific heat capacity, which is C, and it says the piece of iron is at 250 degrees Celsius, and then it cools down to a temperature of 170. Okay, so you need to think which of those is the final temperature and which of those is the initial temperature. Okay, so this is going to be Ti, the 250, and then this one is going to be Tf. Okay, so again, we just use our mc delta T equation. We go to plug in. We have the mass is 12, specific heat capacity is 450, and then I'm going to expand delta T out because I know delta T is T final minus T initial. T final is 170 minus T initial, which is 250. Okay, that's a parenthesis, by the way, that not a 1. And so now I'm just going to type this into my calculator. 170 minus 250 times 450 times 12, and I get again a pretty big number, negative 432,000. Okay, so again a pretty big number. Notice my Q value is in fact negative, which is what I would expect because the temperature of the iron is decreasing. I would expect a negative value of Q, and again, Q, heat is not a vector, it is a scalar, and so this negative doesn't indicate direction in the traditional sense, but it does indicate that heat is leaving this piece of iron. Okay, so that is example 2. Alright, so now you should have enough background information to work on your 2 worksheets. Just a couple hints about your worksheets. Some things to keep in mind, of course, you have your Q equals mc delta T equation. You also want to remember that efficiency is output over input. That might come in handy. And that power is energy over time. That's measured in watts. And remember, 1 watt is 1 joule per second. So those are just some equations that might help you with worksheet number 1 and number 2. Please let me know if you have any other questions.